section we want to talk about the property of the Kramer row lower bound. We define the Kramer row lower bound in the last section, and we give two examples and investigate the Kramer row for the different function of the parameters. So this is the for the unbiased estimators. We have that one, and usually have these conditions. So if you want to find the unbiased estimators which satisfy this inequality transfer the equality, if you find, for example, T star which variance is equal to this lower bound, it is UMVUE. In the example we find that some function have of theta has the estimator which is variance attended the lower bound, and some of this is not attended the lower bound variance of these estimators. In this part we want to check which condition is satisfied if this equality in 3.2 is attended. The remark says the equality attended if Tx and rho over ln theta ln fx, the differential fx is linearity relation with probability 1, which is come from this part of the proof. You know, inequality comes from this part with the Cauchy-Schwarz inequality. So in the Cauchy-Schwarz inequality, when this one is equal 1, when the t and partial differential of ln fx has a linear relation. So if they are linear relation, this inequality transfer to equality, and the variance, and this one is, that one is the equality, and the variance of the t is equal to lower one. So Tx and the equality in 3.2 is attended if this is linearity, or we have a function a theta and b theta which satisfy of that one is the linear function of theta. If you get the integral of both sorts of equations, we have that equation, because if you get derivative of both sides, we can find that one. So if take expectation if you take exponential from two sides, we have that one which is the exponential family. Conversely, if you have exponential family, we find that rho equal rho ln f theta is a linear function of Tx, and the equality is satisfied. So we find only from the exponential family we have this property. If you look of the two examples, we find the binary and Poisson distribution are the densities belong to the exponential family. Another point should be look is the the unbiased estimators of tweeted attends the variance of the unbiased estimator tweeted is attended Kramer or lower bound if fx is belong to exponential family. We can find x, this is exponential family, and when you take the derivative of both sides of this equality, you can find that one. If you want, we look for the unbiased estimator of tx. So here tx for the unbiased estimator of expectation which attended the Kramer row. So if you want find the function which the variance of its unbiased estimators is attended Kramer row, it should be linear to expectation of tx. For example, here for this example, or that one, because it's very simple. You know here, if you want to look of the Poisson is e minus theta x factorial theta square theta power x, we can write expectation xl n theta, but tx is equal to x. The expectation of t of x is equal to theta, so for theta we can find the unbiased estimator which variance is equal to lower bound, and we here the x bar is that one, because the expectation of x bar is theta. So but for example e power minus theta, we haven't this solution. We should use another methods to find u, m, v, u, e. But for some distributions the regularity condition 1, 2, 3 is not satisfied. For example, the example first, the x1 to xn is random sample of uniform theta which is density function equal to 1 theta 0 less than and theta. If you calculate the expectation of derivative of ln fx square, we can find that one, or you have variance of t is greater than square theta square over n. But y is the maximum x1 to xn is sufficient, complete sufficient statistic. This is the density of the y, and is calculated expectation of y as this value. So n plus 1 over ny is the unbiased estimator. If you calculate the variance of this unbiased estimator, we can find by the definition of the variance and write it of that one, and in the final we can find the variance of the new unbiased estimator equal theta square over n plus 2, which is less than this value. So we can the Kramer row said the variance of t is greater than theta square no, but we find the unbiased estimator which has variance less than this lower bound. Why this happens? Because the if you check it, because this condition is not satisfied, when you calculated this condition, we can find that one, and it is this one is not equal of that one, because we have this part only this condition is satisfied if h theta called theta is 0. So that for this example, the conditional we needed are not satisfied. In the general, we can, in the general, if the bound of the sample space of X is depends of the theta, is don't matter, which is the theta less than X less than 0, or 0 less than X less than theta, or 1 less than X less than theta. If the bound of the X is dependent of theta, the Cramer-Rowe condition is not satisfied and cannot be used of this method to find U, MV, UE for parameter of theta. The second subject we want to talk about is the Cramer-Rowe, where the theta is the vector of the parameters. You know, the first time we said the theta is a one value, but if you have a theta 1 to theta k, and we want to estimate, for example, theta 1, if theta is proposed estimators, we can use this lower bound, and we consider theta 2 to theta k as a noise parameters. However, we can find another bound by using these expectations. The basic idea is the Cramer-Rowe lower bound is the correlation between T and rho theta ln fx is not existed 1. So with the in this case we have theta 1 to theta k, we can use of multiple correlation between T and S1 to S SI is that one. Actually, in the before we look of T correlation between T and S1, but you can see here the correlation between T and S1 to SK. So the correlation, multiple correlation between T and S1 to SK by definition is that one with non-zero coefficient R1 to R. If you look of this supremum and variance, we show variance of the S1 to SK by variance of S. So because the expectation of this value, this differential is 0, so that the variance of S equal that value, and the covariance T and T prime S is operating V, which V has that value. If you look at it is equal square rho theta expectation T, and so that this is this value. Therefore, the variance of T, because it is less than 1, so the variance of T on correlation, because this is less than 1, and because this one, that one is less than, we print M inverse V because this is less than 1, we have variance of t greater than variance t. In that one is equal to m inverse v. So we have a new inequality. In fact, in the before we only look for the rho square t and s1, and here replace that correlation with rho t and s1 to s-k. So the lower bound with u3.3 is equal of that, and if the m11 is the when the m11 is the element in the first row and first column of the m, and rho t s1 is the correlation coefficient between t and s1. Because this have this equality, we have that one, and with this example we show the Cromwell row lower bound for the multiple parameters. Let's x has a trinomial distribution. This is the function of the trinomial distribution. If you take derivative of f density fx, we have that one. Theta is equal to theta 1, theta 2, and we have that one. If you calculate the expectation, we have that one. This is 0 is the rule, and the square is the variance. But if you calculated this expectation, have here, and similarity have that one, and for theta 1, derivative of theta 1 and theta 2, yeah, that one. Show the m is the m, and we can find okay, m11 is equal to theta 1, which is the value in the value in the first row and first column of the m inverse. We can find m11 equal that, m22 equal 2, because the m is that one, and m inverse is equal that one. This is one divided by 1, this one, and change that one, and that one inverse. We can find that the first element in the element in the first row and first column is that one, and element in the second row and second column is that one, so that the variance and the Cromwell row lower bound attended by the UMVU is theta 1, theta 2. The UMVU of theta 1 is x1 over n, the UMVU of theta 2 is x2 over n, and the variance of that one is m11, the variance of this one is m22. So the variance, the ambush estimator of the theta 1 and theta 2 attended the Cromwell lower bound. In fact, in this case, the computation is not necessary, because the row t1 to s1 to s-k, we have s1 and s2, only k is equal to, if and only t, if t is the linear function of t1 and s1 and s-k. If you look after look for these two derivative, we find the two derivative is function of x1 and x2. Look at here, is derivative corresponding to theta 1, is derivative corresponding to theta 2 is as a linear function of x1 and x2 as well. Therefore, this family is the density is belong to exponential family, and the relation between these derivative with x1 and x2 is linear, so the variance at the Cramer row lower bound. In this part we define the Cramer row lower bound, the bound for the variance of ambiguous estimators. If you find the estimators which variance attended this lower bound, so that this is the minimum variance, where we find only this property is satisfied for exponential family, was not for all in exponential family, but for some of them. So it's easy way to find UMVUE, but the difficulty is not satisfied for every density function. For example, for density function which x depends, the bound of the x is depend of the parameter theta, it is not satisfied, as we show the example. Or for the distributed density function does not belong to exponential family, this lower bound, lower bound cannot be used. So there are many cases of density function and the parameters which we can't use these methods to find UMU. Therefore, we look of the another methods which is depends of the complete sufficiency. As we said before, the sufficient statistics is the statistic which summarize the information in theta and the complete is said this statistic is unique. So if you find the estimator based on the complete sufficient, we expected to have a minimum variance, because we summarize information all more than other statistics, and it is unique. So in the next section we look for the sufficiency and completeness which define the approach to find UMVUE based on the sufficient statistics, which discuss about in the next